And before we start, some logistics of the tutorial. If you would like to, you can actually like follow along the tutorial with me. Like it's a set of Jupyter notebooks, and if you want to have an interactive tutorial, go through exercises, write code as we go through the tutorial, you can use the My Binder link that I've posted in the Q&A. uh, it will it will open up a Jupyter Lab interface for you, something like this. If you have not worked with Jupyter notebooks before, I'll just put in some pointers in the middle of the tutorial, so don't worry about that. And this is a repository which hosts all the material, and it's much cleaner on the website. And in this tutorial, we'll look at an introduction of NetworkX, the API of NetworkX, uh, and also the goal of this tutorial is to develop network thinking, that you should be able to go from raw data to get a mental model of what is a graph, what is a network, and how to model it. So for that, we'll first look at network API, and we'll also try to cover as much as possible from the algorithms part. And if you have done this before, like if you are familiar with the NetworkX API, or if you think I'm going too slow, feel free to go ahead. This We have a lot of material here. This could easily run into like 5 or 6 hours of tutorial. So if you have worked with NetworkX before, you can just skip part section 1 and 2 and 3, and you can directly jump into bipartite graphs, linear algebra, and we also have a bunch of case studies which use all of the tools that we have learned here and applied to some real world networks like Game of Thrones and the US flight network. So before starting, let's just look at how you can directly jump to the binder link. So if you go on the website, the tutorial website, every chapter will have this launch binder button at top of it. You can just go ahead and click it, and it will open a screen like this for you. You can just look at the logs, and this may take a couple of minutes for you, but after that is done, you should be able. You'll end up with something like this, and uh, let us know in the Q&A if you have any questions about that. If not, we'll move ahead and start the tutorial. So until now, the talks had an overview of what are networks, how they're using networks, and different applications of networks. But let's just quickly have a very like a mathematical definition of what is a network, or as is referred as graphs in graph theory. So for a network, you need two things. You need a node, a set of nodes, and a set of edges. Nodes are these certain entities in a graph, and edges define the relationships in the network. So if you like, this is how it's usually defined, and this could be a set of nodes, and E, which is relationship between different nodes, is edges. So right now, if you see that a relationship is defined between two nodes, it's also possible to have a relationship between 3 nodes and 4 nodes, but that's currently out of like standard network science, and not standard, but standard graph theory. So we will not go there. But our definition will uh, pretty much define, for today, we'll focus on this definition of networks. So let's have a quick look of NetworkX. So first question is, why NetworkX? Why not something else? It's because, in my opinion, NetworkX has a very beginner friendly and very mathematical API. Some things just work. Like it, the API is what it's supposed to be. If you give it to like any graph theorist, they'll be able to figure out what's going on just by looking at the API. And if you remember from the NetworkX talk, we talked about a data model, which is basically dictionaries of dictionaries of dictionaries and dictionaries. So this is how you usually define a graph object, and like G is just a variable name. It can be anything you want, and if you want to access nodes of a graph object, just like a dictionary, you do something like g.nodes, and node one is the reference of that node. It could be an integer, it could be a string, it could be another graph, it could be another another image. So it could be pretty much be any hashable object. If you don't know what hashable in Python is, that's perfectly fine. It's just a technical detail. But with a NetworkX graph, you can pretty much put in anything as a node, and you can form the relationships between them. And that's one of the powers of NetworkX. It's very versatile. It's not just that you need integers or you need certain data types. It's very versatile, and you can build up on top of that. And the other important part of a graph is an edge, which is usually this is how you can access it. And there is a certain difference between how you would do if it were a dictionary of dictionary, but you can use the standard dictionary lookup too. But this is the g edges node 1 comma node 2 is the recommended way of looking up edges. So I guess enough talk about the data model. Let's jump into some code. These are our standard imports, and let's load some data. So this is a network which it's a small network of around 30 people, 30 students in a class. And the network is built up in an interesting way. It goes to every student in a class and asks, would you want to do this activity with this person? And every student gives answer to these three questions, and they'll select their favorite person. So as person A would say, I like that person, I want to play tennis with that person, I want to go swimming with that person. And uh, so, so the controversial part of this network would be, just because A wants to do something with B, that does not reciprocate. That does not mean that B wants to do it with A too. So there are some interesting things that could happen there. And let's just jump into what this graph is that we have built right now, that we have loaded into our graph G. So the first thing we'll look at is the type of graph. So if we do type of G, let's just type it out, then we get something called a digraph. Digraph is just short for a directed graph, and a graph with directions and edges is known as a digraph. So, for example, A can say that A is pointing towards P when they ask, when they tell them this is a person I would like to do this activity with. But that does not necessarily mean that B also wants to do that activity with person A. A more general example of this would be something like Facebook and Twitter graphs. So if you build up the friendship network of Facebook all around the world of all users, just if a person A is friends with person B on Facebook, that also means that person B is friends with person A. So it's an undirected network, the Facebook social network. And if you're on Twitter, just because I follow person A, that does not necessarily mean that they follow me back. Just because I follow Barack Obama, that does not mean that they will follow me back. So that's the quick difference between a directed graph and a undirected graph. A directed graph is signified by digraph in NetworkX, and the other one is just a graph, which is signified by graph, just graph. And there are two other major graph types that we have in NetworkX. That is multigraph, which is, you can define a multigraph like this, and a multi-directed graph, multi-digraph. So as the name suggests, multigraph creates multigraph graphs which allows multiple edges between two nodes. So a quick example of this could be something like a airport network, where every airport is a node, and every edge signifies an airline which flies to the node, which flies between the two airports. So if you want to compress all the data, all the flight data in a country to a graph, you would need something like a multi-directed graph. If a plane flies, if there's a flight from New York to San Francisco, then first of all, it's a directed flight, because just because there's a flight from point A to point B, that does not necessarily mean that there's a flight from a point B to A. In this case, like in a good airline network, it would always be the case, but there's no guarantee of that. And we need the multi part, because multiple airlines can fly from one airport to another. So this is our another graph type. So uh, once we have the data in, we would also like to see the data, how it looks like. So if we want to access all the data inside a graph that we have created right now, let's start with nodes, which in this case would be the students. So if we look at g.nodes, it gives us something called a node view. So node view is something which is based on ticked views, and it's again a Python technical detail, so no need to worry about that. So g.nodes will give us this set of nodes and the set of IDs for us for the students in the network. And like suppose it had like 10,000 nodes, and if you do g.nodes, it will print out like 10,000 different nodes, and you don't necessarily want that always. So if you try, let's just try to print the first 5 nodes, and as you'll see, you'll get this error. So right now we get this type error when we try to slice this node view that we had, and like there currently the node views don't support slicing, and so to counter that we just cast that to a list, which is so we just create a list out of that node view, and then we just look at the first 5 elements of that, and we get our the first 5 elements of the graph. But when I say the first n elements of a node or of a graph or anything, it doesn't really make any sense, because it's a graph. Nodes of a graph is just a set of nodes. They don't really have an order in that. So you can't say, I want the first 5 nodes, I want the last 5 nodes, I want the middle 5 nodes. It's just the way of ordering in which you inserted the nodes into the graph. They could mean something if we are dealing with temporal graphs, but we are not dealing with them right now. But in normal graphs, this is just like, you're just picking 5 random nodes from a collection. That's what it signifies here. So we can also look at, suppose if you just want to look, how many students we have or how many nodes we have in this graph, we can just do a length of g.nodes, which is basically doing running length on an iterable, which is g.nodes. And the other thing is that we need to see is that we also have data associated with every node. So in this data set, every node, like in this case, every student had a gender to n. In this, it's either male or female. And if we look at our list, we'll get this data out. And if we don't cast it just to look at the node view, we get something called a node data view. It's similar to a node view, but it also prints out all the attributes of the node. In this case, it's gender. It could also be just their name, or which city they live in, which what's their home address. Like you can add more. You can keep on adding more data to the nodes. And just like we could also, just like a dictionary, if you do g.nodes, it gives us the node view. But just like a dictionary, if we want to access the first node, the second node, or like the 10th student in the class, we can do g.nodes.10, and it will give us all the attributes that our 10th node has. And and if you look at the data structure closely, it's pretty much like a dictionary. So suppose if you want to iterate through all of the nodes and get their data out, get their attributes out. So we can do something like for n comma d in g.nodes with the data, if we want the data. And then if we just do print n comma d, you'll see that it prints out all the nodes, the node and their attribute dictionary, which is in this case gender.male and so on. So there are a bunch of exercises if you, in this notebook, but we won't like you could go you could try to solve them right now, but we won't really do that. uh, and you can do this after this tutorial. So suppose we want to summarize a node metadata. Suppose we just want to count how many males and females were represented in this graph. So we can do something like going back to our dictionary representations. We just need to run this, right? We just need to get we just need to get all of this out and count male and female. And for that, let's just uh, quickly do this. And what we care about is the dictionary and what's in t.gender. And let's create a list comprehension out of this. You'll see that now we at least have, for every node we have, it's like what's the gender here. And let's do from collections import counter. If you haven't seen this before, that's perfectly fine. It's a very it's a beautiful thing that basically saves you writing 5 more lines of code, and it will return you a counter object which basically counts the occurrences of each of every object in a list or any other iterable. So we see that there are 12 male entries in this data set and 17 female entries in this data set. And this is just something to check our answers if we were doing the exercise. So now we have seen how to work with node and node attributes and their data. So let's look at the other important part of a graph, which is an edge. So just like nodes, if you want to get information about the edges, we just do g.edges, which will give us this nice long list of all the relationships in this network. And we'll just go to the 0, 5. So let's just look at the first 5 to make it a bit more cleaner. So we have these relationships in our network. And if we do the length part, we get that there are 376 such relationships in the network where where we have that a student A has selected student B for a certain activity. So let's also look at the data that we are storing. So this count represents how many times student 1 has selected student 2 as a partner in their activity. And we have this count 1, 2, 3, and it could it usually it will be between 1 and 3. And when we talk about this count attribute, this dictionary can have pretty much anything. It can have count, it can have, this is in, normally you would see something like weights. So if you have a weighted network, this is where the weight actually goes in NetworkX, where you have where you have this edge attribute dictionary. So suppose if we just want to select individual edges, so suppose we just want to see what's happening between 1 and 2, you can use this and it will print out everything that's a dictionary, that's a data dictionary on the edge from 1 to 2. And just to be clear, because this is a directed network, okay, in this case it worked out the same, but just because it's a directed network, that does not it's not necessary that what 1 comma 2 signifies will also be from 2 to 1. So that is something that should be kept in mind. So what happens if we try to find 15 to 16? It gives us a key error. This happens when you try to access the edge which does not exist. So if you look at G15, if if you want to look at edges for node 15, oops, yep, edge, this typo. Oops. Let's do this later. I'm not sure what's happening there, but yeah. So if we look at G edges 15.16, we see that if there's no edge, it will return you a key error, which means that the edge does not exist. And this is again an exercise where just like we did the summarization for edge metadata, we need to, just like we did summarizing for node metadata, we can also look at edge metadata. And we won't be doing this, but you can look at the solution in this notebook later on. So now we loaded in the graph data. We we looked at the nodes and edges. Now the time is to manipulate the graph. So suppose a new kid joins the class and they have their own choices. So we should be able to add the node and add the new relationships that they formed when they joined the class. So in NetworkX, we do g add node will give you an option to add nodes in the network and add edge, which you need to provide a node one and node two, which is from where you want to add an edge. This will provide you with this provides you with a function to add edges. And if you look at this part of the API, this basically lets you add arbitrary data to a node. So if you remember, we had gender as a data point. So if this could be like a gender male, this could be their name, their actual name. This could also be their address. And uh, and for adding edges, we can just do g add edges node one, for example, from student A to student B, and this could be the weight, like this could be a weight, this could be how many, for example, in an airport network, how many flights are there. This could be count in the case of our student network, of how many times they have said that they like doing this activity with them. And so like Python, in Python terms, this is a keyword arguments that just pass into the network, and it basically explodes inside, and you can pretty much add whatever you want. So let's just do a quick exercise. Suppose we want to add a new student in our graph. This is a diagraph that we already have constructed. Let's add a new student, and let's name them 30, and let's say that they are male. And let's add another node, which would be, let's call them 31, and let's the gender be female. And if you look at our nodes now, you'll see that 30 and 31 have been added to this network, but we we haven't really connected them with our network at all. So let's add an edge. But before that, let's quickly look at how this looks like. So NetworkX has inbuilt drawing functionality too. So you can use nx.draw and pass in a graph object, and it will print out a not so nice looking, in this case, image of the graph. But you can see that this 30 and 31 are far away from everyone in the class because they haven't made any friends yet, maybe. So let's make sure that they are friendly now. So let's just add an edge because both of them are new. So maybe they'll probably be friends with each other, which is 31, 30 and 31. And remember again, because this was a directed graph, just because 30 is friends with 31, that does not necessarily mean that 31 is friends with 30. So we need to add the back edge too. And let's just make them a new friend in our class. That, let's see, 7 is friends with both of them. If we do that, and if after doing this, if we draw our graph again, we see that this is our newly added people in the graph, and now they are part of the network. So uh, the next part is just some coding patterns when working with NetworkX graphs. So because g.edges, g.nodes are pretty much treated like dictionaries, List comprehensions are pretty powerful to work with your graph, and something like so if you want to extract an attribute like we did with the gender part, you can just do something like you can write list comprehension, which is compact, which is very Pythonic, uh, uh, and it's pretty readable, and that is the same thing with iterating over edges with list comprehensions too. So like this was the basics of a NetworkX API, where you can manipulate the graph with add edges. You can also remove edges if you want, and for that you can look at the for further reading you can look at the NetworkX API reference, which is available at networkx.org, and you can just there's a tutorial too where you can have a bit more information about this, and then you have the general API reference, which basically tells you about all the algorithms, about the graph generators, and how to work with them. So going back, let's quickly look at visualization too. So NetworkX has some visualization built into that. I couldn't really. I mean, unless it's for like really small graphs, it's perfectly fine. But if it gets bigger, it gets it's not so pretty. For example, if we try to draw our previous network, I mean, you could see that this is a network which is pretty dense, but it's very hard to figure out what's happening there. Like you can't make any claims out of this. Maybe if you add labels, let's see what happens then. And again, nothing, like you get a bit more information that maybe 18 is someone who is not into the core structure of the graph, but again, you don't get much information out of it. Like there are certain things that you could do with it to get some more information out. You can maybe make this a bit more prettier with smaller nodes with not so thick edges, but 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 there are probably better ways of getting visual information out of a big graph. So let's look at some different types of visualizations, not just the canonical way of how to present a graph. So one of my favorites is a matrix plot, and it does what it says. So it basically prints out a graph as a matrix, and if so a graph is usually presented in two ways. One is an adjacency list, and one is an adjacency matrix. The standard data structure in NetworkX, which is a dict of a dict of a dict, is it's basically an adjacency list rather than an adjacency matrix. But uh, adjacency matrix are good to work with, especially when they are dense graphs, which means when there are a lot of different connections between nodes. And for example, if we just look at this plot, believe it or not, this is a graph, and this is the same graph that we had here. So there are certain things that we could figure out just by looking at this QR code, if you may. So if you look at if you look at the diagonal of this matrix, we see that it's constantly empty. So in this graph, blue represents 1 and yellow represents 0. If we look at the diagonal, it says there are no connections between graph itself, between nodes themselves. So what does that mean? So for a matrix, for an adjacency matrix, if you want to if you want to look at that adjacency matrix, just imagine every block is a node on on this side as well as on the other axis, and if there exists an edge between them, then it's the matrix is turned one, the entry is turned one, and this if the diagonal is full of zeros, that means that there are no self edges, which I think is a very good thing in this case, because if you remember, the initial question of the data set was, who would you like to spend time doing X? So it seems like no one is narcissist enough to just say, I just want to play my by myself, no one deserves me. So that's a good thing that there are no self edges here. And the other thing that we could look at is that this matrix is not symmetric, which means it's a directed graph. Because if A says I want to spend time with B, B does not say that necessarily. So there are certain properties that you could just look at a matrix plot and figure out. And this would be very hard if you have something like this. It would be very hard to figure out if it's a like how people are interacted or how nodes are interacted in a hairball like this. So matrix plot gives us that information. and and graph visualization is a active research field. So like when people come up with new visualization formats, because it's 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 okay to plot maybe 100 nodes, 200 nodes, 300 nodes, but as soon as you go into like thousands or 2000, 3000s of nodes, it gets hard to have informative visualizations. So people have come up with things like an arc plot, which basically like you can group nodes. So this could, for example, these are the males and these are the females, and then you can uh, and then you plot the relationships between them. And something like this is very nice if you want to see if there are a lot of in-group connections. For example, you can see that this area is a bit more denser than like the in groups between, for example, the green and the purples. So our plot is a good basis for that. And another point, like these visualizations are not present in NetworkX. They are in something called NXVis, which is a library written by Eric Ma, like the other author of this tutorial. And they have some nice plots if you want to check out. And if you just take this arc plot and you pull them in a circle, you get something like a circus plot. And this again gives us information about in-group activities. So if something like if the middle part of this graph was empty, then you can pretty much say that there are hardly any in-group activities, like out-group activities. Sorry. So if all the edges of all the purple nodes are connected to each other, and if all the edges in green are connected to each other, see a very you would see a not so dense connections here. And this is one of my favorite plots. It's a Hive plot, and it gives a lot of information at the same time. And for example, in this case, it gives you intra-group connectivity and the intergroup connectivity. So every node is duplicated twice here. So like these are the males and these are the females, and this is how they connect intergroup, and this is how they connect to different to people in the different group. And like there are some interesting patterns that you could see. For example, it seems like there are like not all boys are friends with girls. So like for example, certain nodes have no outgoing edges to this group. And it seems like they're just a couple of popular people, and this is not something that you see in this network. And like the same thing about the intra network connections. It seems like uh, the red one is much more denser than the blue one. I mean, these are things that you could figure out because of this visualization. So just drawing, just drawing a hairball is a good first step. But if you want to have informative visualizations, it takes much more than that. And NetworkX currently does not have things like this, but there are other libraries that are built on top of NetworkX, which gives you these nice features. And like feel free to ask any questions in the Q&A if you want any visualization specific questions, and if you have any visualization specific doubts, I would point you towards some nice links. And once we're done with visualization, the second part is the analysis part. So let's look at some certain algorithms of and how they are implemented in NetworkX. So contract contact tracing, it's a very, I guess I mean, now it's just getting old, that COVID-19 is spreading, and epidemiology is a very strong field which uses network science. And suppose you just want to find you just want to find people and quarantine them because they are super spreaders. So what you need to find are important nodes in this network. So so instead, so if, for example, in our current case would be someone who works a retail job, someone at the hospital, because they interact with so many people, they are an important node. And we need to make sure, that's why, vaccine rollout pretty much all over the world focus on them first. So the in any contact tracing network, you need to make sure that uh, you need to make sure that you you find these important nodes. And how you define importance is a very different, it's like there's an active research area which, how you define importance, a very very initial way of uh, doing this would be, just to count how many people you interact with, which is usually what's done. And we'll have a quick look of, how you can do that with NetworkX. And luckily, we have this nice data set which was collected in a conference. And so, so how it was collected was, if two people, like I think everyone had a beeper on their shoulder or something, and if two people talk for more than 5 seconds or something, then they had a then they had a connection between them. And so you have this conference where, people talk to each other, and if they are close enough to each other, then they're close enough that, they can spread if if they can if they have some disease, they can spread it if if it's communicable by air. So I guess very appropriate for for these times. So let's just look at the network. And if you notice, this graph is just a graph, not a directed graph, because if I'm talking to you, if I can spread the disease to you, and if you have it, you can spread it back too. So this is not a directed graph. And let's just look at some quick stats. So we have 400 nodes in this network, which means we have 400 participants in this conference, and they have and we have 2,000 around 2,700 unique connections between them. So let's just go with our first first thing that, we thought, how to find important nodes. Let's just look at how many neighbors they have. For example, in a conference like this, famous people, or famous people, or like an old professor would have a high neighbor. They'll have a lot of number of neighbors, because, they'll talk to a lot of people. People will come to them and talk to them. Or an extrovert person who likes to, just talk to everyone, like they'll have high importance. like I do importance in quotes, because it pretty much depends on how you define importance. It could be just the raw number of neighbors, or it could be a complicated mathematical formula you come up with. And there are a lot of ways of calculating importance. Let's just quickly look at one of them. So if you want to get the neighbors of, for example, node 7, it will return you something called a dict key iterator. If you like a general advice, if you ever find things, d key iterate dict key iterator, like a generators object or anything object, just cast it with a list. It will give you what you want. And so for example, the node 7 has interacted with 5, 6, 21 these different people in the conference. And uh, if you if you want to find the total number of let's just look at total number of uh, like for example, total number of connections neighbor 7 had, the user 7 had, we have 7. If suppose let's go 10 is 10. uh, like the node 20 interacted with 4 people, node 50 interacted with 33 people. So maybe, maybe this person is someone who just talks to everyone in maybe they are one of the organizers who have to talk to a lot of people in the conference. So again, in this case, so we would like to, in this exercise, we basically go through all of these neighbors and try to create a rat list of who's the most important person in terms of how many neighbors they have. And this is something that is known as, we won't do this exercise, we'll just jump to the answer. This is something that is known as degree centrality. And degree centrality is just a fancy name. It just means take all of my neighbors and normalize it by the total number of possible neighbors I can have. So for example, if you have nodes with if you have 10 nodes in a network, if you have 10 participants in a conference, I can, and I interacted with only two of them, but I can technically interact with nine of them, like, except myself. So you just normalize it by n minus one, where n is the number of nodes. You end up with something called degree centrality. And for example, we create this, let's just create this panda series which will hold which will hold the degree centrality thing. And if we sort them, we can find who are the important nodes according to our definition. That, if an important node is someone who has a high who has interacted with a lot of people. So according to our quick analysis, we say that node 51 is an important person. Let's just go back to our let's just go back and actually look at how many nodes it's actually interacted with. If you remember, let's just do list. Okay, so that's a lot of them. So let's calculate the length. We see that node 51 has interacted with 50 different people in this conference. And so if you if node 51 had COVID, then we had to, like, that is the person we need to, like, make sure that they are quarantined. So this is a way of, how you can run contact tracing apps, and like find who are more like people who should not be out, or like, make sure that they get the vaccines first in this scenario. And then the other nice thing that uh, you can look at, how degree centrality is distributed. So this is a ECDF plot. And this is this is how, as you can see, that most of the nodes, like so this side is a fraction of nodes, and this is our degree centrality. So most of the nodes are not that important per se. They don't interact with a lot of people in this network. But we always have these leaders in our network, which will interact with a lot of people. Another way of thinking about this would be something uh, like a Twitter network. In Twitter, not like majority of people won't have millions of followers. Like if we go from our graph theory talk to Twitter talk, neighbors would basically translate to followers, and most of the people won't have millions of followers. And so you will have something like this, where most of the people are, like, like you have this certain pack of people which is ahead of everyone, but majority of the people would be somewhere here where where they're not that central in the network. And yeah. So, and talking about quickly talking about plotting is, once we let's wait for the plot. Yeah. So this is a nicely done plot of our graph. So just imagine if we try to plot 370 nodes and, like, 2000 edges, it would be a mess of a hairball. But this is something that looks nice. And uh, the other interesting thing about the data set is that we have the data in order. Like this, like nodes come in as nodes come in the network as they come to the conference. So one thing that we could kind of suppose, this is like 9 a.m. and it goes all the way to 5 p.m. That's suppose that's how long the conference is. If we look at this network, we can kind of figure out that people who arrive together kind of stay together. So if, for example, if someone was at the conference in the morning, and if someone came to the conference in the morning, that does not necessarily mean that doesn't mean that they interacted with a lot of other people, because we see that they didn't interact with this bunch of people a lot. If we see something, we see like a hole here, so it just means people stayed in their own like communities, and the community was defined by when they came into the conference. So in this case, visualization is an important thing. This is something that you could figure out by running like standard network analysis and tools, which you can see in the later notebooks. But if we know how to plot the right thing, we could actually figure out just by looking at the picture of what's happening. So plotting is a very important subject. So it's so how like thinking so thinking how to model the network, how to plot it, which attribute signifies what. These are very important things. Just by just by calling just by calling algorithms, or standard network measures, wouldn't necessarily give you the insights that you're looking for. But something like this can just uh, give you some quick insights, and give you some quick results what you're looking for. So we are pretty much all out of time now, and I would just encourage you to you can go through this. You can go through this whole book, which is a collection of Jupyter notebooks. We just did chapter 2, 3, and almost 4. And the good part is that it has a lot of exercises, and it's if you are someone who who likes to code rather than listen to people, I feel like this is the best. This is a really nice resource for people who are just starting working with network science and Python. And please let us know if you have any questions or doubts. Thank you.